Hey guys, so I'm gonna do this video. I got tired of hanging up stuff in my room. It's currently the night of open house, and so I decided to make a video. That way I don't have to decorate anymore. So we are going to start talking about inductive reasoning. Okay, so we're getting to the part of chapter 1 where it's not going to be review anymore. We're going to start talking about what we call logic, reasoning. You'll hear different words like that. There's different types of reasoning. Inductive reasoning is just one of those. Eventually we're going to go over deductive reasoning. You don't really need to remember those words necessarily. You just have to remember what to do. So before we start, make sure you take notes. Okay, so I will not give you a grade if I see that you didn't watch the video. So I put these videos through Edpuzzle, so I can see if you watched the whole video. I can see if you watched half the video. So if you copy your friend's notes, well, you're not going to get credit for it. Okay, so make sure if you're taking the time to watch this that you at least write down the notes so you get credit for it. It's easy points. It'll keep your grade up, and you get extra credit at the end of the quarter if you do all your videos, so that's definitely worth it. All right, so we're going to get into inductive reasoning. All right, inductive reasoning is super simple. You do it all the time. Okay, inductive reasoning is where you make a conclusion based on a pattern. Okay, so if I tell you 3 numbers and I say 2, 4, 6, finish the pattern, you're probably going to tell me 8 because we're going in order of skipping every other one or giving me even numbers in order in which they come. Okay, so that's me using inductive reasoning to make a conclusion based on a pattern that I see. Okay, so when I look at this first example, this is going to be one of the simpler ones. Find the pattern and use it to solve for the next 3 terms. Okay, so first we have to figure out, okay, what's happening here? So I can look at it a few different ways. I can say, okay, well, in order to get from -2 to -8, I have to add -6 or subtract 6. Okay, but in order to get from -8 to -32, I don't even have to figure out what it is because I know it's not 6. All right, so we know we're not adding. Okay, so what do I have to multiply to get from -2 to -8? I would multiply by 4. And then I'm looking at, well, how do I get from -8 to -32? Well, if I multiply by 4 again, that's going to give me -32. So here we are multiplying. I'm going to use that way it doesn't look like a plus sign. Multiplying by 4. Okay, so the pattern is multiply the previous term by 4. So that's the first part. So find the pattern. We got the pattern. Now we have to use that to solve for the next 3 terms. So all I'm going to do is I'm going to start with the -32, and I'm just going to keep multiplying by +4. So -32 times 4, so this is term 1, 2, 3. So term 4 is going to be -32 times 4, which is going to give us -128. And then term 5, well, I'm going to take this -128 and I'm going to multiply that by by +4. And that I'm going to get, so -128 times 4, that's going to give me -512. So in order to get term 5, we multiplied -128 by 4. So in order to get the next term, which is the last one we need because it said just find the next 3 terms, so term 6, we are going to do -512 and multiply that by +4, which is going to give us -2048. Okay, that would be our final answer for that type of question. The hardest part about this question is just finding what pattern it's actually using. Once we find the pattern and it asks for a certain amount of terms, we could have went through and just multiplied by 4 50 times if it wanted the next 50 terms. It sucks and it's a lot of work, but it's easy work, right? Because the calculator will do it for us. So let's look at what we just did there. So what we did was we made a conjecture. So a conjecture is a rule based on the pattern that you see. Okay, so it's the rule that is made based on the pattern found. Okay, what that means is and this is the sucky part about inductive reasoning, realistically, all of what we just did, so that part right there, that could be wrong. Okay, a pattern is capable of switching up or not being true throughout the entire statement. That's why we have the ... right there, because we don't really know what's happening after that negative 32. We're making a conjecture and we're making the conclusion that the pattern holds true for the entire statement no matter how far it goes, that it will always continue to multiply by 4. But we don't necessarily know that that's what happens. Okay, so we're going to look at example 2. Okay, it says find the pattern and use it to draw the next image. So again, we have to make a conjecture because we don't know what happens. And I'm going to try to get fancy with my computer here in order to do this. So we have to look, okay, so in this situation right here, I have one of those shapes. Here I have 3 of those shapes. Here I have 5 of those shapes. Okay, so 1, 3, 5. If we were to guess what comes next, if we were to make a conjecture on what's going to happen there, well, our pattern is 1, 3, 5. You're probably going to give me the next odd number, which is going to be 7, right? So the pattern would be to add 2 shapes to the previous image. Okay, and it says use it to draw the next image. So what we would do is we would take this, and I'm going to have to paste it. It's not going to let me move it, is it? Come on. Nope, okay. You would draw it 7 times. We'll just freehand it here. 1, 2, 3, 4, 5, 6, 7. Oh, that's beautiful. That I know it will let me copy. So once I go in and draw that, it is going to end up looking like this. So it doesn't have to be perfect. And in ones like this where you have to draw it, all you need to show is that you have 7 of them, because that shows that you understood the pattern went 1, 3, 5, 7. Now, again, because this is a conjecture, we don't know that this is necessarily going to be true. Okay, it is something we're assuming. It's almost like when you find a hypothesis, you're hoping that it's true, you're saying that it could be true, but it could eventually be proven wrong. Okay, so then we look at how do you prove a conjecture. So proving something false, easiest thing you can do, because you have to find one situation where it's false. Okay, so in order to prove a conjecture wrong, it only has to be wrong in one situation. It could be correct for every number except for one of them. It's going to be false. In order to prove it true is a little harder, because then you have to take the opposite of that. So you have to show that whatever the pattern is, that it holds true for every situation. Okay, so there can't be one situation where it's wrong, because we know if there's one situation where it's wrong, well, that proves it false. Okay, so when we look at examples like that, so what we have to try to find is called a counterexample. Okay, a counterexample is an example that proves something wrong or that goes against what you're saying. So when I look at part 1 of example 3, all prime numbers are odd. Okay, well, prime numbers are numbers that only have itself and 1 that go into it. So we've got 13, we've got 7, we've got 5, but all of those prove that it's true. But what if I tell you 2? 2, the only numbers that go into it are itself and 1, but 2 is also even. That's all I have to do. I found 2, I found the one situation where it doesn't work, done. It's already proven wrong. Okay, for part B, same thing. I just have to find one example where it doesn't work. So let's just plug in random numbers for A and B. So what if I've got A equals 3, B equals 4? Okay, so I would have 3 plus 4 squared equals, and I'm trying to prove that. We don't know if that's true. 3 squared plus 4 squared, okay? So 3 plus 4 is 7. Remember, parentheses first. And then that's going to be 49. 3 squared is 9 plus 16. 16 plus 9 is 25. Does 49 equal 25? No. So this right here would be my counterexample. I don't even have to check to see if it works for anything else. I just know that it doesn't work for that, so it can't be true. In the very last one, if the product of two numbers is positive, so if we multiply two numbers and it's positive, then the two numbers must both be positive. Well, it's partially true in the fact if two numbers are positive, so if both, I'm going to abbreviate here, numbers are positive, then the product will be positive. Okay, but what if both numbers are negative? Okay, so let's think about that. So both numbers are negative, so we'll use 3 and 4 again. Negative 3 times negative 4. Well, when I multiply two negatives, we know that it's a positive, so that's going to be positive 12. That right there, that's my counterexample. Okay, so proving that a conjecture is true is a lot harder than proving that a conjecture is false. Because like I said, in order to prove that it's false, you only need one scenario. But in order to prove that something's true, you have to show that it works for every single situation that's out there. All right, so that's inductive reasoning. That's the first type of reasoning that we will go over. Make sure you understand this part right here where it says that a conjecture can be false. All right, so it's not necessarily going to be true, but you're taking a pattern and saying, if this pattern continues forever, this is what is going to happen. Okay, so we'll do a few examples in class tomorrow. We'll work on finding patterns because, like I said, that's going to be the hardest part. Once you have the pattern, life is super easy, okay? So make sure you have notes. If there's a spot that you didn't understand or a spot where I lost you, make sure you highlight it, star it, do something. That way you remember to ask in class at the beginning tomorrow. And if you don't have questions, then you can just get started on the worksheet.